All right, so let's get started. So what exactly is CAN to begin with? CAN stands for Controller Area Network, and it's a protocol that's used a lot in automotive, embedded systems, and robotics. So that's what it is in a nutshell. But the main part that is a bit more complicated is about figuring out why we want to use it and how it works. So before I get into the technical details about CAN, let's get a bit more intuition about why we would want to use it over other protocols that exist. So let's take a look at this sort of configuration that we have, or the scenario. We have a bus, which is a communication channel that you can connect a bunch of devices to allow communication between them. And the reason why you want to use a bus is this reduces the amount of wires and makes things a bit simpler in your system. But the thing with a bus is that only one device is able to request access to that bus. So that's for good reason. You don't want to read bad data, and you don't want to write bad data either. So only one device is only be able to communicate with the bus at a time. With that being said, in this 4-device configuration, the question then becomes how do we determine which device should have access to a bus at a given time? Especially if all these 4 devices are going to be communicating at the same time. The natural instinct is probably just to think, all right, base it on timestamp. And you could argue that, all right, you can narrow it down to the nanoseconds and say, all right, device 1 should talk first if it has a faster timestamp. The issue with that approach is that if device 2 was, say, your steering wheel, and it sent an error message to the bus saying that, all right, something's wrong with the steering wheel, but the device 1 was just, let's turn on the lights, then we can't guarantee that error message by the device 2 will get processed by the bus. So timestamp may not always work in this case, especially in real-time systems where safety is required. So how do we actually determine which device should have access to a bus? This is what arbitration is going to cover. Arbitration is the process of determining what device should have access to a bus. So without getting into the technical details of the CAN message itself, I'll talk about that later in another slide. But within the message, there's an arbitration field or ID within the message. This arbitration ID or identifier is going to assign a priority to that message. And the way that CAN handles the arbitration process is that the lower the ID is, the higher the priority it is going to be. So from this example, if all 4 devices were to talk at the same time, device ID of 0 would talk first, followed by 2, followed by 3, and finally by 5. In this way, we can guarantee that the highest priority message will be serviced first by the bus. And that way, you can ensure that it's read by the bus. So you can imagine why this is really useful for automotive systems. So that way, we can guarantee that high priority things such as your steering and your engine are able to be serviced immediately in case something goes wrong, compared to lower priority things such as your lights and horn. So this is why we have CAN, because CAN is able to support this arbitration process within its protocol. So from the previous slides, I showed a generic bus, but I hooked it up in a certain configuration. And that's because CAN has some associated hardware with it. So just want to clarify that CAN is not just a software protocol that you have on your computer, but there's also some associated hardware. So in the wiring, there's your typical power and ground connections that you will have in pretty much every protocol. But the 2 main ones that are going to be transmitting and receiving your data are the CAN high and CAN low lines. Now, at the end of those wires, you notice that there's 120 ohm resistors. 120 ohms is just the standard that has been determined by a lot of companies and organizations, but you may see some fluctuations with the actual terminating resistor value. But the main question is, why do we have these terminating resistors? The first reason is just to reduce the amount of oscillations that's happening on those wires. So near the end of those wires, there's going to be a lot of oscillations. Having those terminating resistors is going to help reduce those it's going to help reduce those oscillations that you have on the wires. Second reason is that these resistors can act as a pull up or pull down resistors. So in analog to digital interfacing, there's a certain threshold for your voltage in order for something to be determined a logic 1 or a logic 0. If a voltage exceeds that voltage threshold, then it's a logic 1. If not, it's a logic 0. So having these resistors as a pull up or pull down, a pull up resistor will take a voltage on that line and pull it up to a logic 1. A pull down resistor is going to pull that voltage that you have on the bus down to a logic 0. So these terminating resistors will help regulate to make sure that the voltages are correct and that you're getting that voltage threshold that you want. And the next piece of hardware is a CAN transceiver. This is an interface between the CAN protocol controller and the wires. It does two things with receiving and transmitting. So it's going to receive your signal and convert it into bits for something that the bus can understand. And then it's also going to transmit the signal by converting your differential signal back into something that your computer can actually read. And I won't explain too much about the hardware that's going on within the CAN transceiver, as it's quite complex, but the main takeaway here is that this is just going to be an interface between the CAN protocol controller and the wires that you see on the bus. So now let's talk about the actual message layout for a CAN message. Most of these are a lot of meta information, and I won't be covering some stuff because some of it's a bit more advanced, and this is an introduction to CAN. But the main thing that you should probably care about if you're working on the interface is the arbitration ID, DLC, your data, and some of the CRC and ACK. So the arbitration ID, like I mentioned before, this is a field where you would assign the priority to that message. It's a maximum of 11 bits. And then the DLC, that stands for your data length code. This is going to be how long your data is in bytes. And of course, after your DLC, you have your actual data, which is a maximum up to 64 bits. The next field is the CRC, the cyclic redundancy check. This is going to make sure that your message is fine, and there's going to be checking for transmission errors. Different systems can implement the CRC a bit differently. I think the way that GM has provided it is by using something called a checksum. So you sum up all of your data, and then you take up the 2's complement to make sure that your data looks right and you're transmitting it correctly. And finally, the last one that is relevant is the ACK, or acknowledge bits. These are set initially to 0, and then on the receiving side, it's going to set these bits to 1 in order to acknowledge that it has received this message properly. If the acknowledge bits are not 0, then you probably would not have to take in this message and you may just ignore it. So pretty much the main ideas about the message layout. The other ones are more so just extra things for hardware and for configurations, but I won't really get into them because a lot of the CAN interface that we'll talk about later on already does this for us, so we don't have to worry about it as much. Okay, so I just want to take a break before I get into the application side of CAN and how WATonomous specifically uses it, because there is quite a bit of theory that was covered in these slides. So if anyone has any questions or wants some clarifications on some parts, feel free to ask.
Oh, I had two questions. One is there a standard for CAN to handle transmission errors? Like if the CRC doesn't check out, what do we do?
Yeah, so I think in that case, sometimes we would just retransmit the frame.
Is that a standard thing? Like, can we trust that the system will do that itself, or do we have to do it ourselves?
Oh, good question. I think my best guess would be that it would just try to retransmit based on the system, but I think I probably would have to take a look into that a bit more though. But I
Okay.
would, based on my best guess, that I would just try to resend it.
Oh, cool. Another question is the receive bits. So in a CAN, there are multiple nodes, and it's like a publish subscribe kind of bus. So you have one publisher and multiple subscribers. Who sets that acknowledgement bit?
So I guess this is pretty much the receiver that would set the acknowledgement bit. So like you would have to still send it to a specific destination at the end of the day, right? Like even if you wanted to send it to multiple like subscribers or nodes, right? Then I would assume that you would just have to send it to different. You send it to your first destination, and then you send it to your next destination. Because at the same time with the bus, right? You can only one thing can access it at the same time. You're not going to be sending the same message to every single one. So I think that it would just use of your device message.
Oh, really? I thought it's the other way around. I thought it's broadcast based. Like devices will broadcast messages, and all of the clients will receive messages at the same time.
Yeah. So this is also like a bit more advanced, but I think there is a possibility to like broadcast to every single device on your CAN network. So I think there is a way for you to actually broadcast it, but I'm a little fuzzy about that one because I haven't really had a situation where I had to like broadcast everything to a network, but I feel like there is a way to definitely broadcast information. But I think more or less it's just like one way.
I see. Wait, on a CAN network, there are no concept of like node IDs, as far as I understand. Like, there's no way to specify destination.
The sorry, like the destination.
Yeah, like you said, when we want to transmit the message to multiple clients, we need to do them like sequentially. But I don't think there's a way to identify the recipient. Like,
Yeah, so that's also another advanced concept with something called a remote frame. So in this message format, the RTR is like a remote transmission request, and you set this bit to 1 if you want to send a remote frame. So what a remote frame is going to say is that it's going to try to get the source or make a request to who has a certain arbitration ID, and you would within the remote frame you would have the data be your arbitration ID of your node that you want to communicate with. So yeah, that's something that again is a bit more advanced because we don't really use remote frames, but I think that's how you would handle that situation.
I see, I'm not familiar with remote frames. Very interesting. I just quickly Googled, and I sent a picture in the chat. It seems that all the nodes in the CAN bus would receive message at the same time.
Oh, okay. Well, I guess it was my misunderstanding, but all right.
Okay, cool. Yeah, just wanted
That's good to know.
Okay. Cool. Continue.
Yeah. Anyone have any questions?
Frank, I have a question. Can you hear me?
Sorry. Hello?
Frank, I have a question. Can you hear me?
Yeah, I can hear you. Yeah.
Cool. Going back to the CAN high and CAN low bus lanes, we have the terminating resistors on either side, but you said that it can be used as a pull up or pull down resistors. In the context of CAN, our signal gets transferred by the difference between CAN high and CAN low. So how does the resistor become pull up or pull down?
That's a good question. I mean, yeah, it is a differential signal, like you mentioned, but I think the way that it has is I don't think it can be either configuration. I think it's just like you just have it as one configuration. So I don't think there's a way to make it like pull up and pull down at the same time, if that was your question.
I didn't ask for at the same time. Just, if you were to, for example, let's imagine that you're the only sole receiver for some message. Let's say that you decide ahead of time that your message is only going to be received by a particular node. Other nodes are just not interested in that message ID. So when that node receives the message, they need to send an acknowledgement, right? So they need to either pull up. Yeah, they need to pull up. How does resistor help with that?
Oh, okay. I think I see what you mean. It's a good question. I'm probably have to. I do not know the answer to that entirely, but I would imagine like how the resistor would help. Actually, you know what? Now thinking about it, I don't think it would help that much. I mean, I have to. I'm sorry. I'm a little. I have to get back to you. Answer that.
Sure.
Yeah.
Okay.
I'll you through this. Okay. So now we're just going to go ahead and continue on with the rest of the tech talk, which is going to be more about the application side of CAN and how we use it in the pipeline. All right, so overall, that there are 3 CAN buses that we have on the vehicle. And this is something that has been decided and provided by GM. So we have our low speed bus, which is responsible for controlling the lights, horn, and wipers. We have our chassis expansion bus, which is responsible for controlling transmission, braking, and steering. And then our high speed bus is responsible for controlling the throttle or the torque. So this is going to be controlling the actual wheels and sending the correct values to those wheels. So the main question is then, how does the software drive the car? So Pathline is going to generate some sort of high-level command, such as make a left turn at X speed. At a lower level, they're going to be sending just like the generated float value for the steering angle and generated torque values. But at a higher level, they're going to be trying to send a high-level command, such as make a left turn at X speed. But how does the car actually understand that? The car is only going to understand some signals, but it can't really parse that information correctly. And how does it do that? So this is where something where a middleware or some sort of link would be really useful to decode this information and encode it to something that the bus can understand. So let's take a look at this example. Make a left turn at X speed. We will have a CAN interface that acts as a bridge between the high-level software and the low-level hardware to actually control and actuate the vehicle. So it's going to encode that message into CAN and send data to each bus. So it's going to tell, for example, the low-speed bus to turn on your left indicator lights. It's going to tell your chassis expansion bus to set the steering wheel at this certain angle. And it's also going to tell various other things, such as let's brake if we're moving too fast, or it's also going to tell that let's change our driving state to drive if we're not already in drive. And then finally, it's also going to tell the high-speed bus, send these torque values to each of the wheels. So that's what this CAN interface is going to do. It's essentially going to break up this command that we get from pathlining, encode that message into something that the car can understand. So the message format is CAN, and it's going to send that data to each respective bus. So in our CAN interface stack, there's a total of 8 nodes that get launched up. Over here, you notice there's 5, but The other 3 are more so just for data collection and just for reading from the bus and sending it back to any subscribers of interest. So they're not labeled here because they're not really used for controlling the vehicle. So we have three main things to separate it into, one for low speed, chassis expansion, and high speed. We pack the lights and horn control into just one file. And then our chassis expansion has its 3 primary functions split up into 3 different files. So one for steering, one for braking, and one for controlling transmission. And then finally, our high-speed bus controls the torque and throttle. And just as a precursor, the CAN interface is written in Python 2.7, which is why there's the .py file extensions on those files I've listed here. Now, one thing to note is that the high-speed bus is a bit different, and there's some specific things that we have to do to make sure that we're able to send our torque commands safely. So this is what we need to do. We need to get into autonomous mode. We need to tell the car that we're giving control to the computer instead of having a human take over. So in this flowchart diagram, there's a lot going on, but the main key things to take away from it, and in the diamonds, the left diamond that you see, that's the first state or first thing it needs to check. We need to make sure that the request to turn on cruise control is authorized before we can get into autonomous mode. The next diamond that you see on the right is to make sure that cruise control is set up properly. In other words, is the hardware okay? And if it is, then we are able to get into autonomous mode. So we need to get into autonomous mode in order to send these torque commands. One, it's just a safety thing. We don't want to accidentally send torque commands if we're not driving autonomously. And 2, it's also another security layer to prevent malicious attacks on the car, saying that let's send torque commands, whatever. So, there's a couple of things that we have to do before we can send torque commands on the bus to make sure that we're driving safely and to notify the car that we're going into autonomous mode. So this pretty much concludes the entire tech talk about CAN. We discussed some theory about the CAN bus and talked more about the application side. So yeah, that's pretty much the entire tech talk. Thank you for joining. I hope you learned something of value. And yeah,